Well, hello. Hello, this is review of the Chapter 7 Study Guide A, that is. Study Guide A. This study guide is already on your module with an answer key, and now I'm making 4 to 5 videos to cover all of the study guide. Although I am going to go over the study guide in class, make sure we do it in class together, step by step and problem by problem. I'm also creating videos so those of you at home who would like to study more independently can also have some videos to practice with. Okay, so again, you can print the study guide. I send it to your parents via Talking Points, and I send it to you via Canvas, via email and announcement. And again, the answer key's on there too. So video number 1 was an overview of the entire study guide in its sections. Video number 1 also covered these 6 questions. Video number 2 was dedicated to this graph. So graphing a linear and exponential function, seeing what it looks like, and telling us some important facts about that. The next page. Video 3 was questions 8, 9, 10, and 11. And now here we are, the 4th video. And we are on some great questions here. Now, although I was not born in Eureka Springs, that is where I grew up. Yes, I do have a Southern accent. I love a Southern accent. My mother has a Southern accent. So I grew up on a military base, actually, in Taipei, Taiwan, which is where I was born because my dad was in the Navy. My parents separated, and then my mom moved me to her great-grandparents, so property, well, her grandparents, my great-grandparents, and I lived on a farm in Eureka Springs. So that's why I did a Eureka Springs, Arkansas question. So if you've never been to Eureka Springs, it is quite beautiful. It's a beautiful area, okay? So here we go. The population of Eureka Springs, Arkansas can be modeled by P equals 18,739.92 T, where T is the number of years since 2015. So this equation represents information in Eureka Springs, Arkansas in 2015. So what is it telling me? It's telling me this is how many people lived in Eureka Springs in 2015. It's telling me because this is under $1 that the population is decreasing. If this was a number above $1, we'd know that the population was increasing. Let's read the next questions. What was the population in 2015? Oops. 2015, the population was 18,739. Let's keep going. Is the population increasing or decreasing? Well, because this value is less than 1, we know it is decreasing. So we know that it's definitely decreasing. So because B is less than 1, we're going to go with decreasing. Oops, Ms. Miller should spell that correctly. Decreasing. The next question is, by what percent is the population changing each year? Well, how much under $1 is 92 cents? So if you put it in your calculator, 1 minus 0.92, you're going to get an 8%. And it's an 8% decrease. So every year the population is decreasing by 8%. What was the population in 2018? Well, we already know the formula for 2015, so let's write that down. I just need a new T for time. I can't put 2018. They want to know, in this 3 years, how has the population changed? You're going to put this into your calculator. Use that special cool button that will raise the 3 up to be an exponent, and then hit the equal sign. Now, do I have it done? I surely do. The answer that I have is 14,592. So in 2018, we can put it here, I guess, it's 14,592. The key to this question is, did you answer all the parts? You got to answer all the parts. Did we say the population in 2015? Check. Did we say the population in 2018? Check. And we just used the formula that they had. Did we indicate that the population is decreasing because that value inside the parentheses is less than $1? Check. Did we say how much of a percent decrease? Also check. We answered every stinking question. Nice. My suggestion is that you do the next one by yourself. So you could pause this video, give it a try. TRY, baby. You got a TRY. If I'm doing all the TRY, I'm the one doing the learning. So I'd like you to stop the video and try this one on your own. Go. Cool. Let's check it out. I hope you tried it yourself. So the value of a ring can be modeled by the exponential function this, where t is the number of years since 2015. Sorry, 2005. Now there is a mistake on this. This should also say 2005 right there. So if you have one of my old versions, I tried to catch that mistake quickly, but I may or may not have I caught the one I posted, but I already made a gazillion copies for kids that says the wrong number. So we know that in 2005, this is the value of the ring. Well, let's see what it means. In 2005, that ring was worth $15,000. Yowza, that's a very expensive ring. And what does this B value tell us? Is the value of the ring going to increase over time or decrease over time? Remember, if the number inside the parentheses is bigger than $1, we're talking a value that is appreciating. So the value is going up over time. If this value in the parentheses is under $1, like 89 or 92 or 75, it would be depreciating. The value of the ring would be going down. Okay, cool. So what was the value of the ring in 2005? Again, correct that. It was $15,000. Nice. Is the value of the ring increasing or decreasing? It's definitely increasing. And the reason we know that is because our B value is greater than 1. What's inside that parentheses? It has a growth factor, something that's bigger than 1. Cool beans. Next. By what percent is the ring value changing each year? Well, how much above $1 is $1.03? It's a 3% increase each time period. And lastly, what is the value of the ring in 2012? So we already have the formula, which is lovely. We don't even have to think about it. We just use this already set up formula. Now we have to figure out a time period. So it's 2012 to 2005. You could use this in your calculator. You could do 2012 minus 2005 to see how many years, but it's 7. And you're going to put this in your calculator. And I did put a free scientific calculator on the post for this study guide for your Chapter 7 exam. It's a great little free calculator I found online. Works very well. So we know that this is going to go up in price. If you put it in your calculator, you will get 18,448. If you got that, congratulations. Perfect. So let's flip this over and look at the back. Awesome. So when my dad was of ill health, I traveled back to the South, because that's where my family lives, except my mom. And I noticed that there was this thing growing all over everything. And in the South, they have this very aggressive weed. So this is a real life situation. I'm not quite for sure how to pronounce that, but I would say kudzu. So there's this aggressive weed that is growing all over everything. It literally will grow over a tree and smother the tree because the tree can't even get sunlight. So it literally just kills everything it grows over. And it's spreading. And there's no way to eradicate it or get rid of it. It's just everywhere. So we don't want this to spread. Spread would be a bad thing. We would want it to decay or go away. Okay? So spreading this would be bad. Decreasing it would be something that's good. Okay? So we have this aggressive weed that's spreading in 2 different towns. Each town provides an equation that represents how they have handled the situation. Town A represents their spread of the weed by exponential function this. That's interesting. So they have this many of the plants, and this is telling me that is that growing? Is it spreading more, or is it decaying? Think about it. And town B represents their spread by this. They have the same amount of plants, 8,673, 8,673. But this one has a B that's a very different number. Let X represent the same time period. So we could be talking about a month or a year, a decade. They're the same, no matter what. We have to answer the following questions. Are these towns doing an effective job of stopping the spread of kudzu? Explain. And which town is doing a better job? So again, let's talk about, if we're talking about 8,673 plants, this number right here is very meaningful, the one in the parentheses. If this number, B, is greater than 1, that's bad. It's spreading more. We don't want that. We don't want that spreading more because it's going to kill all vegetation around it. If the B value, what's inside, is less than 1, we know that's good. It's less spread, right? It's actually decay. It's declining. It's not spreading at all. It's decay. This one's spreading because this one's growth. More is growing. Decay, this one is, we're getting rid of it. So one of these towns has spread still, and one of these towns has a little bit of decay. So we got to talk about, are these towns doing an effective job at the spread of kudzu? Let's talk about town A. Do you think town A is doing a great job? No. It's still spreading. That's a growth B. That's a growth factor of above 1. It's still spreading. So these plants won't be 8,673. It's going to be like 9,000 or something. It's still spreading. So that's not good. So we're going to say town A is a no. Their B value is greater than 1, and the weed continues to grow. Whereas town B, let's check it out. Ooh, under $1. We have less. We have decay. The next time period, this number is going to get smaller. And you can even use it on your phone. Like try a 2 there, try a 3 there, try a 4 there, try a 1 there, try a 2 there, try a 3 there. You're going to see that the plants here increase, the plants here decrease. And we don't want this weed to spread. It's a bad weed. It's bad. So town B is doing a better job. Is doing good. Their B value is less than 1, which is decay, also known as less plants. So which town is doing a better job? Town B, as it has a decay factor of 0.99. Cool. Nice. Because it has a 1% decrease. This one has a 1% increase. 1% increase, 1% decrease. And we want this weed to decrease. Okay, so it's important to decide if something is something you want it to get bigger or something you want to get smaller. So I'm going to stop the video here. The last video will cover questions 15 and 16. Have a great day. Bye.